A cat sleeps between 12 and 16 hours a day. Some sleep up to 20. This is not laziness. It is the operating system of an obligate carnivore whose entire physiological architecture is built around explosive, high-cost predatory effort, followed by extended recovery. Every position, every location choice, every shift in sleep depth is a direct expression of that architecture. Crepuscular rhythm. Domestic cats are not nocturnal. They are crepuscular, biologically primed for peak activity at dawn and dusk, the precise windows when their primary prey species, small rodents, are most active. Felis sylvestris libica, the North African wildcat ancestor of all domestic cats, evolved this rhythm over millions of years in an environment where hunting success during low-light transition periods was the difference between survival and starvation. The suprachiasmatic nucleus, the brain's internal clock, regulates this rhythm through light-sensitive cells in the retina. As ambient light shifts during dawn and dusk, melatonin levels drop sharply, triggering alertness. Between these windows, melatonin rises and the cat enters sleep. Owners who describe their cat as crazy at 3 a.m. are observing a domesticated version of this rhythm that has partially shifted toward human schedules but never fully abandoned its evolutionary baseline. The cat is not malfunctioning. Its suprachiasmatic nucleus is running a program that predates human civilization by several million years. Polyphasic sleep architecture. Humans consolidate sleep into a single long block. Cats do not. Feline sleep is polyphasic, distributed across numerous short cycles throughout the 24-hour period. A typical cat completes between 13 and 20 individual sleep cycles per day, each lasting 15 to 113 minutes. This pattern has a direct predatory logic. A single long sleep period would leave a wildcat vulnerable and unresponsive for hours. Distributed short cycles allow for rapid reactivation. Within seconds of waking, a cat's cardiovascular and musculoskeletal systems can reach full predatory readiness, a physiological feat that requires the specific neural architecture that polyphasic sleep maintains. Within each cycle, cats move between two distinct states. Light sleep, characterized by slow-wave brain activity, occupies roughly 70% of total sleep time. REM sleep, during which the brain consolidates learning and processes sensory experience, occupies the remaining 30%. During REM, cats show rapid eye movement, whisker twitching, and occasional vocalizations. The muscles remain largely paralyzed, the same rhematonia observed in humans, but small movements persist. The loaf position, the tucked position, forepaws folded beneath the chest, tail wrapped around the body, eyes partially closed, is universally recognized. Its function is thermoregulatory and defensive simultaneously. By minimizing exposed surface area, the cat reduces heat loss. By keeping the limbs beneath the body rather than extended, it maintains muscular readiness for rapid standing. In wild felid populations, this position is adopted when an animal is alert but resting, not fully committed to deep sleep, monitoring the environment with residual sensory attention. The domestic cat uses it in the same context: unfamiliar environments, new people in the home, or any situation where the cat has not fully assessed its safety level. A cat that consistently sleeps in the loaf position with a human present, rather than in an exposed, extended posture, is communicating a specific trust calibration. It is comfortable enough to rest, but not comfortable enough to fully relinquish defensive readiness. Exposed belly sleep. The exposed ventral posture, cat lying on its back, abdomen fully visible, is the most physiologically vulnerable sleep position available to a felid. The abdomen contains no skeletal protection. All major organs are exposed. In a wild context, this posture is only adopted by an animal that has thoroughly assessed its environment and concluded that threat probability is low enough to justify the vulnerability. Cortisol levels in cats, measured during ventral exposure sleep, are consistently lower than in any other sleep position. The hypothalamic pituitary adrenal axis, the stress response system, is at its most suppressed. The cat is not performing trust. It is physiologically incapable of being more relaxed. Owners who interpret this posture as an invitation for belly contact are misreading the signal. The exposed belly communicates environmental safety, not not a request for tactile interaction. The majority of cats will immediately retract from belly touch even when sleeping in this position. The sudden contact activates a reflexive defensive response that the cat did not choose to initiate. Location selection. Where a cat sleeps is as diagnostically meaningful as how it sleeps. Elevated locations, shelves, the tops of refrigerators, high furniture provide the predator's preferred resting vantage. Maximum sight lines, minimal approach vectors from below. This is directly inherited from arboreal resting behavior observed in wild felids across Africa and Asia. Warmth is the second major location driver. A cat's thermoneutral zone, the temperature range at which it expends no energy on thermoregulation, sits between 30 and 38 degrees Celsius, significantly higher than the typical human living environment. Cats seek heat sources because remaining within the thermoneutral zone during sleep reduces metabolic cost and conserves energy for predatory activity. This is why cats sleep on laptops, on recently vacated human seats, on electrical equipment, and in sunbeams. These are not affection displays. They are precision thermoregulatory decisions. The choice to sleep near or on a specific human is a separate calculation. A bonded cat sleeping in physical contact with its owner is accessing both the thermoregulatory benefit and the oxytocin-mediated comfort of proximity to a trusted social partner. Both factors are operating simultaneously. Twitching and dream states. During REM sleep, cats exhibit visible motor activity, paw twitching, whisker movement, tail flicks, vocalizations ranging from chirps to growls. Research using feline EEG, conducted at the Lyon Neuroscience Research Center in the 1960s by Michel Jouvet, established that cats in REM show brain activity patterns nearly identical to waking states, with the motor cortex actively firing while the brainstem suppresses physical movement. When this suppression is pharmacologically reduced in experimental contexts, sleeping cats exhibit coordinated hunting sequences, stalking, pouncing, and prey capture movements, confirming that REM content in cats is heavily weighted toward predatory simulation. The cat is not dreaming in a narrative human sense. Its motor cortex is rehearsing predatory sequences during offline processing. The twitching owners observe is motor cortex output leaking past incomplete brainstem suppression. It is neurologically identical to the hypnic jerks humans experience when falling asleep, a brief failure of the suppression system during state transition. Sleep as metabolic strategy. The volume of feline sleep is not a personality trait. It is a metabolic equation. Hunting at full predatory capacity, the explosive acceleration, the precise strike, is among the most energetically expensive activities a mammal can perform per unit of time. The domestic cat's musculature is designed for maximum short-duration output, not sustained effort. Recovery from that output requires extended sleep. Even indoor cats that never hunt real prey run the same metabolic program. The predatory motor sequences executed during play, the stalk, the pounce, the grab, activate the same muscle groups and neurological pathways as actual hunting. The sleep that follows is the same sleep a wildcat uses to recover from a successful hunt. A cat sleeping 16 hours is not wasting its day. It is maintaining the physiological state that makes those remaining 8 hours of potential activity possible at full predatory capacity. The same strategy that allowed Felis sylvestris libica to survive and eventually become the most numerically successful felid species in human history.